Hello friends, welcome back to our channel. So in today's session we'll see one more concept in compiler design, that is directed acyclic graph. So in our previous session we have seen the complete introduction about intermediate code generation, and that can be different types of intermediate code generation. We have seen the postfix notation as well as three address code and syntax tree and directed acyclic graph, which is a DAG. So in that we have already seen the postfix notation and also the syntax tree, and now in today's session we'll see the directed acyclic graph. So this is usually we can call it as a DAG, directed acyclic graph. And we know that directed graph means, first a graph means it will be having the nodes and corresponding edges, and directed means that edges will be having the direction. Okay, and acyclic means there should not be any cycles. That means if you start from one node, if you traverse all the nodes, it should not end with the same node. So that is called a cycle. So it should not contain the cycles, and it is a directed. And here the nodes in that leaf nodes, similar to our syntax tree, the leaf nodes are operands, and internal nodes, that means which are not a leaf nodes, are operators. Okay, so for example, let us take here A, B, C and D. So we can say this is a graph. Okay, whether it is a cyclic or acyclic graph. So how to know that? So it is a undirected. Okay, it's an undirected. So undirected means if you travel from A to B, B to C, C to D and D to A, so there is a cycle. So starting node is A, and we are traveling and we are coming to the same node. So that is that is nothing but a cycle. So it is not a acyclic graph. So if it is a directed, there will be the directions. Now you can observe. So this is a directed graph because each and every edge is having the arrow. Okay, and each and every edge is having the direction, right? And also if you start with A to B and B to C, and there is no path from C to A, so this is a acyclic graph. So in this we can say the leaf nodes. So we can also say a tree as a graph. Okay, so this directed acyclic graph is similar to a syntax tree. So a reduced memory of syntax tree. Okay, so we can say a tree is also a graph. A tree can also be considered as a graph. Okay, so reduced memory of a syntax tree. So how we can say the reduced memory? Main aim of this one is it will eliminate common subexpressions and recomputational expressions. So the main reason of getting this directed acyclic graph is we can eliminate the common subexpressions as well as recomputational expressions also, and also it will generate the optimized code. It will be used to generate optimized code. Okay, which is a next phase of a compiler. So example, in the last class we have seen an example like a plus b into a plus b. So we have drawn the syntax tree here. We have taken star on left hand side, we have given plus, and here again plus, which is a and b, a and B. So this is a syntax tree. This is a syntax tree. So one thing you can observe here, this term is A plus B. This is a plus B, and this is also A plus B. You can observe here, this is also A plus B. So what happened here, two times we are performing the same operation, so same expression is evaluated two times. So such type of things can be avoided in this directed acyclic graph. So how can we draw this one here, right? So first we'll take an expression A plus B, okay, and then you have to perform the multiplication towards the same thing. So we'll give one more node with a multiplication, and we'll be applying the same thing here. Okay, so this is a direct acyclic graph. So this portion is a plus B, this portion is a plus B, which is multiplied twice. Instead of giving this one, we'll draw this one. This is a directed acyclic graph, and here you can observe there should be a directions on edges, direction on edges. So if we have to draw the directed graph, acyclic graph for A plus B, the plus will be the internal node and A and B will be the leaf nodes and directions towards the plus. So this implies A plus B. A plus B. So for any kind of expressions we can perform this directed acyclic graph, and now we will see a few examples on how can we draw the directed acyclic graph for a few expressions. So one thing we need to remember for constructing this directed acyclic graph is operator precedence. Operator precedence. So which operation should be performed first, which expression should be performed first. For example, we can take A plus B into C. So in this expression, first highest precedence with a star. So first create one node for B, one node for C. So here rules are, whenever you are trying to create a new node, once check whether it already existed with the same value in the tree or not. If it exists, you can make use of that particular node, and if it doesn't exist, or if it changes the value, you can create a new node. So initially there are no nodes. I have created one node for B, one node for C, and I have created multiplication. So give the arrow marks. So this is a B into C. So which result should be further added to A? Okay, because the first operation is B into C, the result of B into C should be added to A. So I'll write a one more operator here plus, and that will be added with A. You can see. So this is a simple directed acyclic graph for the expression this one. For example, let us take one more thing, A into minus C. See, this is the expression, A into minus C. So here minus C, here we are having a two operators, one is a star and this is a unary minus. Minus C is a unary minus. So among these two operators, minus, that means unary operators will be having the highest precedence. So first this should be given. So initially there is no node here, so we can give one node which is minus, that is a unary minus. So that should be multiplied with a A. So this should be multiplied with A. So this is the directed acyclic graph for this particular expression. So hope you understood. So for this we need to know the operator precedence, which operator is having the highest precedence. Okay, so let us take one more example and I'll stop. In our next session we'll see a few more examples. So let us take this example. So A is equal to B plus C, D is equal to A minus E, F is equal to B plus C, and G is equal to F minus E. So starting with the first instruction. So initially there is no node here. Okay, we can create B and C and perform the addition operation. So I'll perform B and C. I'm creating two nodes, performing the addition operation in between them. So This is a directed acyclic graph, so you have to use a arrow marks, okay, directed arrows. And then D is equal to A minus C. So this is A. This is A. Okay. So just for reference, I am giving A, label A. So A means B plus C. So what happens? Next D is A minus E. So whatever the result we are getting with this, that should be applied in this expression. So E should be subtracted from this one. So once again, I'll use minus and I'll use E. Okay, A and E. So this is A and this is E and this is a D. D. Next, F is equal to B plus C. So what is a B here? B. And C here. So already B and C is same. Okay, already B and C are same. And one more thing we have to remember, whether the values have been changed or not. And here you can see, so on RHS, A and D, that means B value, C values have not been changed. Okay, A value and B value and C value has not been changed. The same values we are adding and we are calling it as F. So you can give the same thing with F, label F. So A is B plus C and F is also B plus C. And G is equal to F minus E. G is equal to F minus E. So you can see F is nothing but this one minus E. So here you can say this is also G. It's also a G. So A is B plus C, F is B plus C, D is A minus E, and G is F minus E. So like this we can use, and this is a directed acyclic graph. So what we have done, we have avoided the repeated computations. Here you can see B plus C is repeated and B plus C is repeated, and here A minus E and F minus is also same because A and F are equal. You can see A is equal to B plus C, F is equal to B plus C, A and B, F are equal. Okay, so here two computations are repeated. Okay, there are repeated computations. We are avoiding that one in representing the DAG. So if you are drawing the syntax tree for every expression, we need to draw the syntax tree. So that's why we are calling the DAG is a reduced syntax tree, reduced memory of syntax tree, reduced memory of syntax tree. Okay, so hope you understood this one. Let's stop here, and in the next session we'll see a few more examples of constructing the directed acyclic graph. So just remember, directed acyclic graph, which is one type of intermediate code generator to generate the intermediate code, which gives as an input for the next phase, that is a code optimization. And this will be also useful to generate the code, and also it is a variant of syntax tree. We can also call it as a variant of syntax tree. So both are equal but with a minimal modification. So DAG is a reduced memory of syntax tree, so variant of syntax tree, right? So let's stop here, and if you are having any queries regarding this one, feel free to post your doubts in the comment section. Definitely I will try to clarify all your doubts. And if you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.